Hello Year 10, you need to get a pen or a pencil, something to write on, and a song to time yourself, or a timer, whatever, and be ready for the first little rapid recall task. So pause the video if you don't have those things. Okay, so first job, you need to tell me what are the 3 results from the gold leaf experiment, so what happened to those alpha particles. Then you need to say what 3 things do those results tell us. You need to give a definition of what an isotope is, and you need to tell me what number of protons, neutrons and electrons are in hydrogen, boron, sodium and chlorine. Careful of the atomic masses. So pause the video here, start your song and get those things done. Okay, hopefully you finished your little rapid recall task. I'm going on to my answers now. We've got, so for the experiment, it's quite a lot here. You don't have to have this much detail, but this detail is quite nice. Most of the alpha particles are straight through the foil. Some were deflected by a little angle. Some were deflected by a very large angle, go straight back. This tells us, so straight through, most of the atom's empty space. Some were deflected by a small angle. There's a concentration of positive charge in the atom. And they go back at a very high angle, and some completely backwards, means that the mass and charge is concentrated inside a tiny volume, the nucleus. Then I've got protons, neutrons, electrons for hydrogen, so 1, 1, 1, 1. Okay. Remember, we're just taking the big number from we take the little number from the big number to get the number of neutrons, so 2 take away 1. We've got boron 5, 7, 5. We've got sodium 11, 11, 11. And chlorine 17, 16, 17. Okay. So give yourself some ticks and some pats on the back if you got those right. Now, last time we looked at isotopes and about what our model of the atom is. Okay, we're going further with isotopes this week. Okay, because we can have lots of different types of isotopes, and some of those isotopes are unstable. Okay, and to become stable, they need to change the number of protons or the number of neutrons, or both, from inside the nucleus. And they can do that by emitting nuclear radiation. Okay, by emitting nuclear radiation, you can change the number of protons and the number of neutrons. It will change what element it will be. Okay, but it can become more stable by doing that. And you need to know about 3 radioactive processes. You need to know about alpha particles, beta particles, and gamma rays. And all these isotopes that are unstable, that emit this radiation, are called radioisotopes, from radioactive. Okay, they give out radiation. So, we're going to look at those 3. So, alpha particles. Here's a little diagram showing alpha decay. So we've got some unstable nucleus, some radioisotope, and it undergoes alpha decay, and it changes what this atom is. It will no longer be this thing. So if it was uranium, and it gives out an alpha particle, it will turn into a different element. It will turn into thorium. Let me double check that, but I think it's thorium. Okay, and it gives out this alpha particle. And this alpha particle, the same stuff that was used in the gold leaf experiment, is a helium nucleus. 2 protons, 2 neutrons. Okay, it causes the atomic mass and the atomic number to go down. The atomic mass goes down by 4, the atomic number goes down by 2. It changes what the element is. Alpha particles are big, slow, and massive. Okay, they've got atomic mass. They've got a mass of 4, atomic number of 2. It's got a positive charge, plus 2 positive charge, because there's 2 protons. They're easily stopped, so they can be stopped by a piece of paper. They can be stopped by skin. Okay, they are highly ionizing, very ionizing. They can be used in smoke detectors. So in a smoke detector, you'll have an alpha emitter and a sensor that detects the alpha particles, and it will be constantly detecting these alpha particles all the time. And then when a smoke particle gets in the way, when there's a fire and the smoke particles get inside the smoke detector, and they get in the way of those alpha particles, it will stop the alpha particles from hitting the sensor, and the smoke detector will go, oh, there's no longer any alpha particles, there must be smoke in the way, let me turn on my alarm. Okay, so they're used in smoke detectors. Now, the next one is beta particles. Beta particles are an electron. Okay, similar picture. I've got an unstable nucleus. It undergoes beta decay, and a beta decay is when a neutron changes from being a neutron into a proton and an electron. So it flips. Okay, so if you notice in the picture here, this is my neutron, and it flips colour into a blue, and it becomes a proton. And an electron. Now that electron can't stay inside the nucleus, it's not allowed, so it gets spat out, it's emitted. Okay, now it causes the atomic number to go up, because I've got an extra proton. So the atomic number goes up, but the atomic mass doesn't change, it stays the same, because the mass of a neutron and the mass of a proton are the same. So the atomic mass stays the same, but the atomic number goes up. It changes what the element is. Now beta particles are quicker and much less massive than alpha particles. Okay, it's very close to zero mass. Okay, it's got a charge of -1, just like an electron. It will pass through paper, through skin, but it can be stopped by a few millimeters of aluminium, it's like 5 millimeters. Okay, it is less ionizing than alpha particles. Less ionizing. They can be used for lots of things. They can be used, for instance, in medical tracers. So a doctor can give you an injection that will contain a beta emitter, and then they'll use detectors to see where that tracer goes. So it might be that you would use iodine, which goes into your thyroid gland, which is really important for hormones that you learn about in biology. And that iodine will latch onto the thyroid gland, and then you can use a scanner to detect those beta particles, and you can get a really clear, really detailed picture of what your thyroid gland looks like. That's one example. Okay, they can be used in lots of different tracers. They can also be used to monitor the thickness of materials, so slightly more mundane. They control the thickness of aluminium foil in factories. Now, next one is gamma rays. Gamma rays are different. They do not change the atomic mass, and they do not change the atomic number of an atom when it's emitted. Okay, because they don't have any mass and they don't have any protons. Okay, it's a way of atoms to transfer energy. Now, it normally really happens as well as together with alpha and beta emission. When something gives out an alpha particle, there's a good chance it's going to give out some gamma rays as well. Not always, but sometimes. It does not, on its own, it does not change the type of element that it's been giving it out. Okay, it does not change that element. It's an EM wave, so you'll have heard of it before when we did the electromagnetic spectrum waves. Okay, it travels at the speed of light, has no charge, zero charge. It's very penetrating. It can only be stopped by really, really thick lead, so meters of lead or meters of concrete. It is much less ionizing than both beta and alpha. It's very weakly ionizing. They can be used to treat cancer, and it's called radiotherapy. Okay, now you need to know and understand this picture. This picture shows us 3 types of radiation that you need to know about and what it can be stopped by. So alphas can be stopped by paper, beta can be stopped by few millimeters, 5 millimeters of aluminium, and gamma can be stopped by very, very thick lead. Now, some of them might get through. Okay, reduced by thick lead or thick concrete. Now, in an exam, a popular question, a question that often would come up with, it'd give you this picture, but it wouldn't tell you what's what. It would just tell you, okay, so a particle goes through paper and it doesn't go through aluminium. What type of radiation is it? Is it alpha, beta, or gamma? And you just say, oh, it's beta because it's stopped by aluminium, but it goes through the paper. Okay, so you need to be able to understand. You need to learn this diagram. Okay, now your first job, I want you to have this table. Make it like maybe half a page of AE or half a page of an exercise book, half a page of A4, something like that. Because you don't need to write you don't need to write that much in the boxes, but you need to fill in this table. Okay, the summary table about those 3 types. You need to know the symbol and the name, so I've given you those 2. You need to write down the mass, the charge, what it's stopped by, the ionizing power, and then a basic use. Okay, so only want, a couple of words for the use. You can put more detail if you want, if you know it, but just a couple of words. Okay, so pause the video here and fill in this table. Okay, hopefully you've done that now to the best of your ability. If you haven't filled in some of the boxes, if you couldn't remember some of those bits, that's okay. Just get what you do know into this table, because I'm going to go through the answers now. Okay, so we've got mass of 4, 1 over 2000, so it's very small. A mass of 0, charge of 2, -1, 0. Stopped by paper, a few millimeters of aluminium, 5 millimeters. It's very thick, a lot of concrete or lead is stopped by. Highly ionizing, less than alpha, more than gamma, very low. Using smoke detectors, medical tracers, treating cancer, radiotherapy. So you need to know this information. You need to know some uses, you need to know its ionizing power, you need to know it's stopped by, you need to know its charge and its mass and its symbol. Okay, because in your exam you could be asked to identify one of these types of radiation by its properties, by its use. Okay, now I'm also uploading this little summary page into ClassCharts as well. So this is just a summary page on those 3 types, and it's got some more detail about some uses. Okay, so that's the first half of what we're learning about today. The next thing, okay, can cause some confusion in students. It can really get students a little bit worked up and confused and frustrated in what's going on, how it's going. And it's all, I get it because it's different and it's new, but when you know it, it's so easy. It's so easy. It is dead easy. Okay, so the next part of the video is going to be on nuclear equations. Okay, nuclear equations. So the first thing I want to do is a little bit of maths. Just bear with me. Pretty simple maths. So you've got 20 equals something plus 4. What's the something? Write it down. 6 equals something plus 2. What's the something? Write it down. Dead easy sums. Key Stage 2. Key Stage 1 maths. Key Stage 2 certainly. Okay, so if you're doing primary school. Okay. 20 equals 16 plus 4. 6 equals 4 plus 2. Okay, really easy sums. Now I've written it down slightly differently here. The numbers are the same, but I've just changed the equal sign into an arrow. Okay, 20 goes into 16 plus 4. It's the same on both sides. Okay, this is the skill that you need to use to be able to get tons of marks in your physics paper if nuclear equations come up. Okay, so let's do an alpha particle example first. Now I've made up this isotope of carbon. I know it's carbon because it's got 1, 2, 3, 4, 5, 6 protons. Anything with 6 protons is carbon. So I know it's carbon, but it's got extra neutrons. So radioisotope, it is really unstable. It's got lots and lots of neutrons. It is incredibly unstable. Okay, how many neutrons? How could we work it out? We could count them. Okay, but I also know it's carbon 20. Okay, and I know there's 6 protons and 20 protons and neutrons. So I can do 20 take away 6. 20 take away 6 is 14. There should be 14 neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. I made my diagram properly. 14 neutrons. Okay, now carbon 20 decays by giving out an alpha particle. So here's my carbon atom, here's my alpha particle, and it leaves. So once it's decayed, I get this, what's left over, and the alpha particle. So at the start, I've got my carbon 20. It decays, it gives out an alpha particle, and I'm left with an alpha particle and whatever atom this is. No longer carbon, because it's only got 4 protons. Okay, so this is what I got at the end. I've got my alpha particle and my new atom, my new different atom that's only got 4 protons. How many neutrons does it have now? How many protons does it have now? It's easy to see, there's 4 protons, it's quite quick to count. Hard to count the number of neutrons, but I can do some quick maths. Here's the whole process. So I start with my carbon 20, it decays, it changes into this new atom, and it gives out an alpha particle. Now, physicists, we tend to be a bit lazy. So we won't draw these pictures all the time for all these isotopes. We won't draw them, we'll write the symbols. Okay, so I can write it like this. So here's my carbon 20, it's got 6 protons, it's got 14 neutrons. Here's this new element, I've just called it X because I don't know what it is yet. It's got 4 protons, 1, 2, 3, 4, and it's got 16 as its atomic mass. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and it's got the alpha particle here, which has got an atomic mass of 4, 1, 2, 3, 4, it's got 4, and it's got 2 protons, 2. And here's where that math at the start comes into. 20 equals 16 plus 4. 6 equals 4 plus 2. Okay, I can work out what these numbers are if I know what the carbon is, if I know the numbers of the starting atom, and I know what type it emits. Or if I know what the starting atom is, and I know what this resultant atom, what it's changed into, I can figure out what type of radiation it's given out. Okay, if my atomic number has gone down by 2, it's got to be an alpha particle. It's got 2 protons. If my atomic mass goes down by 4, I know it's got to be an alpha particle because it's gone down by 4. The atomic mass, the total here, so 16 plus 4, has to equal this number here. The mass and the proton numbers are conserved, just like we did with energy being conserved. The atomic number, the number of protons, and the number of the atomic number and the number of mass, it's conserved on either side. Okay, so this row has to make one of those little sums. Okay, and here's just that written out a little bit clearer. So we've got 20 equals 16 plus 4, 6 equals 4 plus 2. Now, whenever I come across nuclear equations in a paper, I would encourage you just to write a little equal sign above the arrow, just to remind you that the maths is dead easy. Okay, dead easy, and you get loads of marks for it. You get tons of marks. Okay, because it can be a bit confusing. Okay, if you let it. Here's another example, and how we can. Okay, so how do we figure out what that X is? We need to look for the atom that's got 4. Okay, we can go along this table and we can see that beryllium has 4 protons. It's not going to be sodium that's got 3. It's not going to be boron that's 5. Okay, its atomic mass, 16, is all correct, but it's got to have the right atomic number. So if we start with carbon and it gives out an alpha particle, the number of protons always goes down by 2, so we can go not boron, but beryllium. If we start with fluorine and it gives out an alpha particle, the atomic number goes down by 2. It won't be, as my point it won't be fluorine anymore, it will go oxygen, nitrogen. If we start with oxygen, it will go down 2 places to carbon. If we start with argon, it will go down 2 places to sulfur. If we start with uranium, it will go down 2 places to thorium. Okay, so it always drops those 2 proton spots, and we can figure out what it is from the periodic table. Okay, here's a different example. We've got uranium turning into thorium. I want you to pause the video and try and answer this. So you need to write down the nuclear equation, start with the symbols. So start with a U goes into thorium plus alpha particle. Then put in the numbers. So write the nuclear equation to help you find out what the isotope of thorium is. How many neutrons does it have? Okay, I'm going to go through the answer slide in a moment. So pause the video if you want to give it a go. Okay, so I write down my symbols first. Uranium equals thorium plus alpha. Okay, then I put down stuff I know. I'm told that there's 238 as the atomic mass of uranium. I can put that in. I'm told that it's got 92 protons. I'm told that thorium has 234. I'm told that it's got 90. I know, because you need to remember, that an alpha particle has 4 as its atomic mass and 2 as its atomic number. I can figure out what that 234 is, because 234, okay, plus 4 gives me 238. I can do that simple calculation. So its atomic mass is 234. And then to find its number of neutrons, we do 2, 3, 4, take away 90. The big number, take away the little number, to give me 144 neutrons. Okay, now this is a high grade question. It's quite high skill. Okay, so it would give you good marks that lots of other students in the country might not get. Okay, so if you're able to do this, give yourself a massive pat on the back. If you're not able to do it yet, okay, we're going to do some more practice over the next in the questions and the task, and there's going to be some exam questions that you're going to go through in the live stream lesson. So don't stress, you'll get it, and once you get it, it's easy. Right, so a similar thing can be done with beta particles. So here's an element of PA. I can't remember what PA is, but it decays into thorium. Okay, it gives out an a beta particle. So this neutron, this blue neutron, turns in, sorry, this white neutron turns into the blue proton when it gives out a beta particle. So it changes the element. And you look at the atomic mass. The atomic mass is easy this time. 234 equals 234 plus 0. Okay, the atomic mass doesn't change. The atomic number goes up by 1 because that neutron turns into a proton. Okay, 91 take away 1 equals 90 because the atomic number of an electron or a beta particle is -1. It's like to do with its charge. Okay, that's the way you can think about it. So 91 take away 1 gives you 90. So we can do a similar example. This is a real isotope. We've got carbon-14. This is using carbon dating, which we're going to learn about in the next couple of weeks. So carbon-14 decays by giving out a beta particle, and it turns into this X atom, which has got 7 protons, and it's got 14 protons and neutrons. So here's the inside of the nucleus, where we've got this neutron changes into a proton and gives out the electron. Okay, 7 take away 1 gives you 6. 14 plus 0 gives you 14. Okay, easy maths. It's slightly different here because it's not an alpha particle anymore and it's got 0 mass and it's got -1 as its atomic number. Okay, but the atomic number goes up, the mass number stays the same. Okay, and here's that example clearly. I'm going to pause my video for a second. So here's that example written out as a full equation. Carbon-14, 6 protons, decays into nitrogen, because nitrogen's the element that's got 7 protons, and it gives out this this beta particle. There's numbers on each side of the equation balance. So 14 plus 0 gives you 14. 6 equals 7, take away 1. Okay. Now you don't need to do nuclear equations for gamma rays. Gamma rays don't change the number of protons and the number of neutrons in an atom, so we don't need to do nuclear equations for them. So, second task is using the time that you've got left over your hour of work. You need to try and answer the practice recall questions. Okay, on this slide. And then on the next slide, we've got the application questions. So these questions 1 to 5. This is all in class charts, by the way. And these questions 1 to 4. Now this one, just have a sneaky look. Okay, this the symbol. Okay, sorry, the HE symbol. It tells us what does it tell us? What is this? Okay, because it's been a bit tricksy here. What is HE? Think nucleus. Think nucleus. This one, the math is easy to remember. We're just filling in the numbers. Put the little equal sign here. This question's a little bit tricky. This is quite hard, so if you struggle with it, don't stress about it. So your task is to try and answer these questions and these questions as much as you can, and then leave like 10 minutes at the end, and I've got the answers, so you can give yourself a quick mark. Okay, so you can give you a quick mark of the work. Okay, so if you've done all your work on these questions now, well and good. If you haven't, you need to pause the video because the answers are coming up now. Here are my answers for the fact recall questions. And here are the answers for the application questions. Okay, well done year 10. Some of you are going to be in school over this week. I might see some of you. You're going to see some of your science teachers. I hope everything's going well at home. Take care and goodbye.